The day we introduced electromagnetic radiation, we said that electromagnetic radiation is a wave. And we know that partially, at least, because it exhibits properties of waves. There were 4 properties of waves that we talked about that day. One of those was polarization. Polarization was that phenomenon where part of a wave gets filtered out. You've got a polarizing filter, and it filters out all the components of a wave but one. It allows only one part of the wave to go through. We did a little demonstration where we had 2 polarizing filters, turned them 90 degrees to each other. It filtered out the entire wave. That's polarization. That's a property of a wave, and it's exhibited by EMR, so therefore EMR must be a wave. Another one we talked about was refraction. Refraction is the bending of a wave. When a wave goes from one medium to another, it changes speed. And as a result of that speed change, the wavelength will also change. In addition to the wavelength changing, the direction will change. That change in direction, due to the change in speed as it goes from one medium to the other, is called refraction. Now, these last 2 that we're going to talk about, we addressed that day. We briefly talked about that first day, but we're going to talk about them in a lot more detail today. The first one, or the third one I should say, was diffraction. Diffraction, if you remember, is the spreading out of a wave. Much like refraction, at least on the surface, but it's not really changing direction. It's just when it goes through an opening or around a barrier, spreading out. Then interference will happen as a result of one wave being on top of another wave. Can't spell it. There we go. When a crest meets a crest, when a trough meets a trough, when a crest meets a trough, we can get constructive or destructive interference. We can get a bigger wave, or we can get the wave canceling out as a result of that destructive interference. This is what we want to focus on today. First of all, that diffraction, the spreading out of a wave, and then second of all, what happens when we get multiple diffractions taking place, and then we get interference as a result of that. So, just a refresher, diffraction is that spreading out of a wave as it goes through an opening or around a barrier. And this is a picture of actual diffraction taking place. You can see clearly that there's waves coming in from the ocean or from whatever it is. Okay, they're going through this little opening right here, and what's happening as they go through that opening, they spread out like this. Okay, I'm exaggerating it a little bit, but you get the idea. Now, diffraction is affected by a couple of different things. The size of the opening. It's affected by the wavelength. We're not going to focus so much on that right now, but just understand that you can get more diffraction or you can get less diffraction, depending upon the conditions that exist. Diffraction is the spreading out of the wave versus refraction. Remember, when you went from one medium to the other, it changed the direction entirely. This is interference. This is what happens when we get diffraction taking place in 2 places. So there's a point source right here. Okay, maybe it's, I don't know, something being dipped in the water like this. Dip, 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 produces circular waves. Okay, maybe another one right here. Or maybe it's just a plain flat wave coming up like this, going through 2 openings and diffracting in 2 places, producing 2 diffraction patterns like this. What's the end result of that? Well, the end result of that is that you get this constructive and destructive interference. You get an area right here that has larger crests and larger troughs than it normally would. That's constructive interference, when a crest meets a crest or a trough meets a trough. Same deal right here, same deal right here. But in between those, you get these areas of destructive interference, where you can see that the crest has canceled out with a trough. Okay, there's nothing there. There's no wave. The wave is gone, because there's been destructive interference, a canceling out of a wave. Now, when we're dealing with water waves, we can physically see this, right? We can look at this from above and see the interference pattern that takes place. If you stand back from this, you can clearly see the areas of constructive and destructive interference. If you're dealing with light, you're not going to see this. And the reason is because the light has to reflect off of something to be seen. We don't see things if light doesn't reflect off of it. So we don't see anything here if this is light. It happens. Light will diffract, light will interfere, but we won't see it diffracting and interfering because it's not reflecting off of anything. So how do we know that it's doing it? Can't see it. How do we know that it's doing it? Let's put a screen over here. If we put a screen over here, then we can detect things. When you have, if this is light, remember, when you have constructive interference, okay, one of these areas where the crests are big and the troughs are big, you're going to see a bright spot on the screen. Right? If you get constructive interference with light, it means it's bright light. It's just you're not seeing it over here because the light's not reflecting off of anything. But if you've got a screen over here to detect it, then all of a sudden you're going to see this bright spot where this line of bright light, this so-called invisible bright light, this not visible bright light because it's not reflecting off of anything, where it actually reflects. You see a bright spot. And then right next to it, you see a dark spot. By a dark spot, I mean it doesn't make, if we had this set up in this room right now, you wouldn't see an area that was black. You would see an area where there was no light, where there was no red light. So by a dark spot, we mean no bright spot. You see a bright spot, and then you see a dark spot, and then you see a bright spot, and then you see a dark spot, and then you see a bright spot, and so on. So on that screen that's set up on the other side of this pattern actually taking place, you see these alternating areas of bright spots and dark spots. Does that make some sense? If you had some screen over here that could detect intensity of water waves, you'd see the same pattern. You'd see an intense water wave right here, and then nothing. And then an intense water wave right here, and then nothing. It's harder to see visible light in between than it is water waves. But it's easier to see light at the screen than it is water waves. So we view water waves in one way, we view the pattern for visible light in another way. This is just another diagram that shows basically the same thing, but maybe in a bit better of a way, just already built for you here. You've got the waves, these plain flat waves going through two openings, and you can see the two diffraction patterns here. As a result of those two diffraction patterns, we get interference. We get constructive interference where crest meets crest, trough meets trough. We get destructive interference where crest meets trough. These black lines that you see on this diagram correspond to the areas of constructive interference. Okay, what do we see at the end there when we have the areas of constructive interference? Well, we don't see anything in between here because the bright light isn't reflecting off of anything. But when it gets to the screen and reflects off of the screen, we see a bright spot. This bright spot that we're going to call our central maximum. Maximum because it's a bright spot, and central because it's in the middle. Right next to that central maximum on either side, we're going to see what we call our first order minimum. It's a dark spot. A dark spot on either side. Now, right next to each of those first order minimums, we're going to see a first order maximum. So we've got our central max, and then a first minimum, and then a first max, and then a second min, and then a second max, and then a third min, and a third max, and so on and so on and so on. It doesn't go out infinitely. It does stop at some point, but it goes out for the foreseeable distance here, for the foreseeable future here. Now the graph, the diagram that you see right here is a graph. It's related very, very closely to what you saw back here. It looks a lot different, but it's related real closely to it. This is actually a visual representation of the intensity of the light. You can physically see by looking at this picture the light. You can see when it's bright red. You can see when it's dark. We're going to call this our x-axis. Okay, everything along that horizontal distance is our x-axis. This is still going to be our x-axis. But this time, instead of looking at a literal representation of the brightness of the light, we're looking at a graph of the intensity. So my central bright spot, my central maximum, shows me that I have the most intense light. It should be curved at the top there. Microsoft Word just wouldn't do that for me. We have our most intense light. And then we have a dark spot where we have our first order minimum and no light, destructive interference. And then we have a first order maximum. It's intense light again. Not as intense as in the middle, but still intense light again. Then a dark spot, then a bright spot. So instead of seeing literally the bright spot, the dark spot, the bright spot, the dark spot, we're seeing a graph of intensity. And of course, where you have a bright spot, you have intense light. Where you have a dark spot, you have a lack of intensity. You have zero intensity. Central maximum, first maximum, second maximum, and so on. We have other names for these as well. The maximums could be called antinodes. Could be called bright spots. So instead of being the first order central maximum, it could be the first antinode, the central antinode, or the central bright spot. Same deal with the first order maximum. Could be the first order bright spot, the first order antinode. The minima could be called a node or a dark spot. The antinodes and the bright spots, the maxima, are due to constructive interference. And the nodes, the dark spots, the minima, are due to destructive interference when crest meets a trough. Here's another diagram that shows the same thing. This diagram is designed to show us what the variables in two equations that represent interference patterns will look like. You have monochromatic light. Monochromatic means one color, by the way, right? Mono means one. Monochromatic, one color. So you got one color of light. It's hitting this barrier right here, going through two openings. As it goes through those two openings, it diffracts like this. It spreads out. As it spreads out, those two diffraction patterns produce an interference pattern, where you get areas of constructive and destructive interference. These blue lines would correspond to constructive interference, where a crest is meeting a crest, or a trough is meeting a trough. Constructive interference. But then in between there, you get areas of destructive interference, where a crest is meeting a trough. Where you've got the constructive interference, hey, if this was water waves, we'd see these nice lines of constructive and destructive interference there. But it's not water waves, it's light. If it's light, we have to put in the screen there. When we add the screen there, we're going to see a bright spot in the middle, and then a dark spot, and then a bright spot, and then a dark spot, and so on. Bright spot, dark spot, bright spot, dark spot, like we've seen in a couple of other diagrams. Now, there's two equations that we have listed off to the side here. I want to identify some of the variables in these equations and reference it to the diagram that you see on the left there. First one, lambda. That's the easy one. Lambda is the wavelength of the light. And it's going to be measured in meters. This would work with water waves as well, but of course that's not our unit. Right? Our unit is electromagnetic radiation, so we're talking about this in the context of light. But the equations are valid not just for light. They're valid for any wave. It's just that with other waves, you don't observe the pattern on the screen. You observe it in between. So lambda is the wavelength of the light that we're using. Okay, done in both equations. D is probably the next easiest variable. D in both equations represents the distance between the two openings. And that's going to be a pretty small distance. A pretty small distance between the slits. What was it in the little demonstration that I did for you a few minutes ago? 0.04 millimeters. 1/25th of a millimeter. And we're usually talking about a small distance here. In fact, we're always talking about a small distance. Usually really small. D is the distance between the openings. And that's going to be measured in meters as well. Our next one is going to be L. L is going to be the distance from the slits, or from the openings to the screen. Now notice I've made that a capital L. There's no reason why I had to make it a capital L other than if I make it a lowercase l as it appears in the equation, it looks like a 1. So I just make it a capital L so that you know it's not a 1. The capital L, lowercase l, it doesn't really matter what you call it. In the end, it's the distance from the openings, from the slits, from the openings, to the screen. And that's going to be measured in meters. These three variables can be a little bit confusing because they're all distances, they're all meters, they're all lengths. We've got to keep those straight. Wavelength, not so much. It's easier to keep straight, right? D and L, hey, those are tricky. Doesn't seem tricky right now, but once you get doing problems, it's sometimes a little bit hard to keep those two straight. When I was in high school, I always got those two mixed up, D and L. The distance between the slits, the distance from the slits to the screen. The good news is, L will always be bigger than D, always. So if you have two numbers and you're getting mixed up as to which one's which, the bigger one is L as opposed to D. Let's look at another one. This one gets a little bit trickier. X. X is this distance, or this distance, or this distance. X can be whatever distance you want from whatever maximum to any other maximum, or any minimum to any other minimum, or any maximum to any other minimum. It can be from any max, the distance, from any min or max to any other min or max. How do you have an equation where you can make x whatever you want? Doesn't that mean that the value of lambda that you solve for can be pretty much a random number? On the surface, yes. But if we go a little bit deeper, we see that the value of n also can be whatever we want. And x and n have to be consistent with each other. N is going to be the difference in max or minimum number. It's just a number. We're going to subtract. And that number n has got to be consistent with x. And if those two are consistent, then it doesn't really matter what value of x you're using, as long as n is consistent with it. So in this case, we'd say x is, well, whatever we measured it to be. It's a distance. Okay, use a ruler, measure the value of x. The value of n in this case, the corresponding value of n would be 2. This would be our central maximum, first order maximum, second order maximum. 2 minus 0 is 2. And this one up here, we'd say n is equal to 1, because it's 2 minus 1. Doesn't matter if you make x whatever value of x this should be, as long as you make n 2. Doesn't matter if you make x this value up here, as long as you make n equal to 1. What would n be right here? Anybody want to take a stab at that one? Going from the first order max on one side to the second order minimum on the other side. What would n be there? We're not going to the first order max on the other side, are we? First order max here to the second order minimum here. This is like 1.5, isn't it? So what are we going to say here? 1.5 minus negative 1. Or you could say 1 minus negative 1.5. Doesn't matter which way you go. We're going to say it's a value of 2.5 for n. 1 minus negative 1.5. If you're dealing with a minimum, tack a 0.5 on the end of it. If it's a second order minimum, it's midway between the first order max and the second order max, so it would be 1.5. 1.5 minus -1, or 1 minus -1.5. In both cases, we get 2.5. So, doesn't matter. Pick whatever x you want, 1, 2, or 3. As long as n is consistent with that, you should get the same answer any way you look at it. One more variable. It's getting a little cluttered here, but one more variable. What are we missing? It's theta, right? Theta is somewhat like x. It's not a distance, it's an angle, but it's an angle that can be measured almost wherever we want. The difference here is that x can be measured from whatever we want to whatever we want. Theta has to be measured from the central maximum. From the central maximum to the second order maximum, the first order minimum, the second order minimum, it doesn't matter. From the central maximum to any min or max. Now, how can we make an angle wherever we want? Well, we just got to make sure that n is consistent with it. So if we're using whatever value we want for x, that's great. Just use the corresponding value for n. Using whatever angle you want, that's great, as long as it's measured from the central max and you're using the corresponding value of n with that. Is that okay? I know it's a little bit confusing right now, especially when you look at what's written on the board here right now. There's a lot written on the board here. But what does it boil down to? Let's erase it real quick and go through it again. What's it boil down to? This is the value of d. Okay, this is the value of d. This is the value of n. Lambda is, of course, the wavelength. So now what are we left with? We're left with n, theta, and we're left with L. Sorry, not L. N, theta, and x. What's x correspond to? X corresponds to, well, whatever distance you want. From whatever max or whatever min to whatever other max or whatever other min, as long as n is consistent with it. To find n, all you're going to do is subtract the maximum number or the minimum number. This is 0, this is 1, this is 2, 1, 2 on the other side. 2 minus 1 is, n would be equal to 1. 1 minus -2 is, n would be equal to 3 in that case. Okay, make x whatever you want, just make n consistent with it. Finally, theta. X is measured from whatever to whatever. Theta is measured from the central maximum to whatever. So from here to here. Or maybe it's from here to here. Doesn't matter, as long as n is consistent with it. In this case, n would be equal to 1. In this case, n would be equal to, what's n equal to there, Parker? N would be equal to 1.5 there, right? Because we're dealing with a second order minimum. A 1.5 minus 0 is 1.5. We left out something, though, this big if, this capital letter bolded if. If, well, there is no if with the first equation. The first equation, d sine theta over n, is always valid. We're allowed to use that 100% of the time. It is not an approximation. It's an exact value for the value of lambda. The second equation, however, is an approximation. It's a very good approximation. It gives you a really good value for lambda if theta is less than 10 degrees. If theta is greater than 10 degrees, then the approximation that this equation gives us isn't so good. The value that we're going to get is going to be too far off to bother using this equation. So, angle less than 10 degrees, you're good to go. Angle that's greater than 10 degrees, don't use it. Sometimes we don't have the angle. You want to determine whether the angle is greater than 10 degrees, you got to either calculate the angle or use a rule of thumb that I've kind of devised. My recommendation would be don't calculate the angle every time because it's extra work. Use the rule of thumb. Here's the rule of thumb. If L is greater than 10 times x, you're good to go. So whatever the value of x is, multiply it by 10. If L is still bigger, use that equation. If L is not still bigger, then don't use that equation. That rule of thumb errs on the side of caution. What does that mean? Well, it means that even if the rule of thumb isn't met, and then you go and you say, oh, I can't use that equation, every once in a while you could have. Every once in a while you could have used that equation. But it'll never lead you in the wrong direction. In other words, it'll never say, oh yeah, you're okay using that equation, and oh, well, it turns out that was wrong, you couldn't use that equation. Use the rule of thumb. It's going to save you work in the long run. I promise you, it's going to save you work in the long run. If L is greater than 10 times x, you're good to go. If it's not greater than 10 times x, then find the angle, and I'll show you how to do that later on, and then use the other equation. Okay, we got a couple example problems here. The first one is on page 689. It says monochromatic light. This is one color. That's good. One color. Okay, when I showed you the little demonstration a few minutes ago, I used red light, monochromatic light, one color light. That makes life a little bit easier for us because when we're talking about wavelength, we only have one wavelength. It's incident on two slits that are separated by 0.3 millimeters. When we did the little demonstration, it was 1/25th of a millimeter, the distance between them. Here it's 1/3 of a millimeter. So it's still a small distance, not nearly as small as what we used. I want to circle this. And then I want to call this little d, the distance between the slits. It says the angle from the central bright spot, the central bright fringe, to the first bright fringe is 0.08 degrees. That's going to be theta. Always has to be measured from the central to whatever. Here it's measured from the central to the first. Don't know the wavelength of light. Now here they tell me n is equal to 1. I don't want you to use the value that they have written down. Here's why. If I draw out the bright fringes here, first central bright spot, first bright spot, second bright spot, third bright spot, fourth bright spot, and so on, they're labeling n is equal to 1 as these values, not as the difference. We want the difference. Now, as it turns out, the difference between 0 and 1 is 1. So n is equal to 1, but not because they say n is equal to 1 there, but because 1 minus 0 is 1. Now, which equation are you going to use? You got two of them. We got d, we got theta, we got n. We're looking for lambda. Which equation are we going to use? Probably going to use the first one, right? That's good, because that's always valid. We don't need to worry about whether L is greater than 10 times x or not. We just use it. So let's try it. Lambda is equal to d sine theta over n. b is 0.30 times 10 to the minus 3, because it's got to be in meters. We don't need to worry if theta is greater than 10 degrees or less than 10 degrees. In the end, it's way less than 10 degrees here. The second equation would be valid. But why would we bother using it when we have all the givens to fit the first equation that we know is always valid? N is equal to 1 then. So let's do the math. Let's say 0.3 times 10 to the minus 3, because we want to be in meters, times sine 0.08. Gives me, divided by 1, gives me 4.2 times 10 to the minus 7 meters. You should expect to get 10 to the minus 7 meters in all of these questions. Why? 10 to the minus 7 meters is visible light. I mean, odds are you're not going to be doing this experiment with infrared, right? You could, but you couldn't physically see it. You'd have to have some kind of other detector, not your eyes. to see the pattern. Is that okay? I'm going to give you 3 questions to work on here. And as you're going through these 3 questions, I want you to pay attention to a couple of things. Okay, 1, units. We're often dealing with units other than meters here. Millimeters, nanometers, centimeters. Okay, convert to meters always. The second thing, pay attention to whether they're talking about maximums or minimums, antinodes or nodes. Okay, if you're dealing with an antinode, whole numbers. Nodes, you're dealing with 0.5s. So pay attention to that. If you see the word node or dark spot or destructive interference, something like that, minimum, then circle it in red. All right, let's give these a whirl and then we'll take a look at them in a few minutes. I want to just take a quick look at 14 and set it up here. Sorry, not 14, number 3, and set it up here. Where did 14 come from? Set up number 3, because this one has a little bit of a trick to it. It says the second nodal line. Hey, nodal line, circle that one. Man, because we're used to seeing antinodal lines, bright spots, whole numbers. Nodal lines have half numbers, 0.5s. So we got to be careful with this. We got an angle here of 0.095 relative to the central antinode. This is going to be theta. We're going to say this is going to be D. We want to circle that millimeters though because we want to convert that to meters. We're looking for lambda. We're not going to panic about the color here, but we are looking for lambda, the wavelength here. What's the value of n? Draw it out. This is your central antinode, central bright spot. 0, 1, 2, 3. We're dealing with the second nodal line. So the angle is measured from the central antinode to the second nodal line, the second dark spot. Whatever theta is here, 0.095 degrees, way less than 10, of course. What's n going to be? Yep, 1.5. Okay, it is so easy, so tempting when we read this question. The second nodal line, n is equal to 2. Okay, read it carefully. Know whether you're dealing with an antinode or a node. In this case, it's a node, so we're going to make it a 0.5, 1.5. So we're going to say, in this case, lambda is equal to d sine theta over n. Okay, we got d, we got theta. We got n now is 1.5. Solve for lambda. This is what we get. Okay, 10 to the minus 7 again. It always is, right? Seems to always be 10 to the minus 7. Let's take a look at another example here. This one says a student measuring the wavelength of light emitted by Krypton gas sample directs the light through 2 slits that are separated by this distance. This is going to be d. But we want to circle that in millimeters because we don't want to be in millimeters. We want to be in meters. The interference pattern is produced on a screen that's 3 meters from the slits. That's going to be L, right? The distance from the slits to the screen. Distance between the second bright spot and the central bright spot is 1.18 centimeters. This is going to be X, the distance from bright spot to bright spot, although we don't want to be in centimeters there. What's the wavelength of the light emitted by Krypton gas? We didn't know what n is too, right? Central maximum, first order bright spot, second order bright spot, third order bright spot. Okay, we're dealing with the central antinode in the second bright spot. 2 minus 0 is same number they give us there, but for a slightly different reason. Okay, n is equal to 2. The difference between the maxima is 2 there. Hey, we want to use this equation, right? Lambda is equal to xd over n times L, because it fits, right? We got x, we got d, we got n, we got L. Good. Use it, right? Except that we have to pay attention to that little if that we learned a few minutes ago. If what? If theta is greater than 10 degrees, we don't know what theta is. If we knew what theta was, we might as well just use the equation with theta in it. Right? So what's our rule of thumb? Is L greater than 10 times x? Let's multiply x by 10. X is 1.18 centimeters. If I multiply it by 10, I get 11 centimeters. Right, 11.8 centimeters. Is L greater than 10 times x? L is way greater than 10 times x here, right? Are we allowed to use this equation? It's an approximation, but at such small angles, it's a really good approximation, so it's good. you're good to go with this. X is 1.18 times 10 to the minus 2. D is 0.264 times 10 to the minus 3. N is 2. And L is 3 meters. So let's do this on a calculator here. 1.18 times 10 to the minus 2. 0.264 times 10 to the minus 3. Let's divide that by, use some brackets here, 2 times 3. 5.19 times 10 to the minus 7. Hey, would you look at that? 10 to the minus 7, visible light. All right. One little word here before I let you do these practice problems. A rule of thumb, right? L is greater than 10 times x, you're allowed to use this equation. What if we did a rule of thumb? What if we multiplied x by 10 and L wasn't greater than 10 times x? Then we'd have to use the other equation, right? But we don't know what theta is. How could we use the other equation without theta? Oh. This is going to be L. This is going to be x. If we know what L is and we know what x is, then can't we find theta? You could do that every time. In fact, that's what I would guess 90% of the Physics 30 students in this province are going to be doing when they see the diploma exam. They're going to look at this and say, oh, I got x, I got L, let's solve for theta. Is theta bigger than 10 degrees or is it smaller than 10 degrees? Oh, it's smaller than 10 degrees. I can use my original equation. Lambda is equal to xd over n times L. That's fine. You can do that. But from my perspective, if we've got a little rule of thumb that works for us, then why would we even bother calculating the angle? Okay, in the end, if we calculate the angle, why do we even have this equation? Why wouldn't we just use the other equation? Once we get theta, you got the other equation that's valid 100% of the time. I'm only going to get theta if L is not greater than 10 times x. If we have to use the other equation because L is not greater than 10 times x, then let's get theta, and then let's use the other equation. But if we can avoid this, if we can avoid using the trigonometry, then let's avoid it and just multiply x by 10 and see how it compares to L. You got that? So if you're doing a problem here in the next few minutes where L is not greater than 10 times x, then do this, use some trigonometry to get theta, and use the other equation. In the vast majority of problems, however, I would say at least 95% of the problems, you won't have to worry about that. L will be greater than 10 times x. But every once in a while, okay, it won't be. You got to be watching. You got to be on the lookout for that. Okay, have a look at the 3 questions that go along with that, please, on page 691. Let's take a little break from working on those problems. You can go back to them in just a moment once we're finished this. This is the end of what we're doing here today. I just want to draw your attention to this just in case you see this. Okay, now, the odds of us seeing it generally aren't that big, aren't that high, because in the end, usually we deal with problems like we've been working on. What's the difference between these 2 pictures that you see up here? Diagram 1 versus diagram 2. Yep. Okay, diagram 2, you see a spectrum. You see multiple colors, right? In diagram 1, you see 1 color. Now, in all the diagrams that we've drawn so far, we've used red board marker, right? We've used a red smartboard marker indicating that it's red laser light. That's the most common color of laser light because most lasers are helium neon lasers that produce red light. They're the cheapest ones. Okay, so that's what you usually see here. But if we use green laser light, then we'd see what we see in the top diagram. Bright spot, dark spot, dark spot, and so on. This would be our central antinode, first order antinode, second, third, and so on. No different than what we've done to this point. Exactly the same. Okay, the distance between antinodes X and L and D and theta and all that stuff is exactly the same as it always has been. The bottom diagram, it's still exactly the same as it always has been, but it can be a little bit more confusing in the bottom diagram. In the bottom diagram, instead of shining a red laser light or a green laser light, as the case may be, through the two openings, in this case, we're shining white light through the two openings. What's white light? Well, it's all the colors of the rainbow, right? Or at least it's multiple colors, more than just green or more than just red. It's more than one color going through. When we do that, just like refraction takes place a different amount depending upon the color, so does diffraction. So in other words, what you get here is an interference pattern for each color, not for white light. You don't see a white first order max, a white second order max, a white third order max, and so on. You see a first order max for each color, a second order max for each color, and a third order max for each color. So what you're effectively dealing with here is white light in your central maximum. That's always what it's going to look like. All the colors of the rainbow in the middle. But as you go out from that, your first order maximum will be the rainbow. Your second order maximum will be the rainbow, and so on and so on and so on. With one difference. The rainbow produced by refraction produces red, orange, yellow, green, blue, indigo, and violet. The rainbow produced as a result of diffraction is exactly the opposite. It starts off with violet and goes through red. So red light refracts the least, red light diffracts the most. Now, if you ever see a problem like this where you've got multiple colors, what I want you to do is pretend you don't have multiple colors. Pick a color. Pick red or yellow or whatever color it is that you have data for, and then ignore everything else. If I've got my central maximum, which is my white light, I'm going to make it yellow just because I can't draw white on white. Okay, that's my white light. And then my first order maximum is violet light all the way through red light. And my second order maximum is violet light all the way through red light, and so on. You can pick either the red light or the violet light or the green light and go with it. Pretend the other ones don't exist. So if you've got a question involving multiple colors like this, but you've got data for the red light, then just erase the other ones. They don't exist. That makes sense? Pretend you just have red light and treat it like you do have one color. Is that okay? Becomes a problem just like you've been working on for the last 6 questions. Just seems more confusing because you got all these different colors. Here's what I don't want you to do. Don't look at this and say, oh, okay, wait a second, I got this. This is the first order maximum. This is the second order maximum. This is the third order maximum. No, it isn't. This is the first order maximum for red and for green and for violet. This is the second order maximum for red and green and violet, whichever color it is that you're dealing with. Is that okay? All right. I'll let you go back to those questions here now to work on page 691. Finish those up for homework if you haven't finished them already, and if you don't finish them in the next couple minutes, right?